Okay. Um, so, in what can only be described as a week long struggle in finding a solution to a certain problem, basically, a kind of an obsession, I came up with this nice theory about the average rating of Goodreads data. So, basically, the probability distribution of books according to average rating. And I'll explain the context soon, but this is what I came up with. This is a massive upgrade from what I've been doing so far. So I also have this in PDF form. So this is the PDF. This was supposed to be my report on the analysis that I did for a course that I'm taking at IIT Kanpur. And this was the original Notion page that I was using to create this PDF. Also, this same thing will be available to you in as a Notion page on the web, right? And yeah, let's just get started. So what is this about? First of all, the Goodreads 10K dataset. This is available publicly on GitHub, and it consists of data like number of ratings, average ratings, 1-star rating, 2-star rating, so on. So there's one books.csv file which has 23 columns, and there are 10,000 books. So those are the rows, and those 23 columns contain these properties of those books. So the number of 1-star ratings, number of 2-star ratings, the total rating count. There's also something called the work rating count, which I do not understand what that is. And also the weird thing is, like, the ratings were adding up to work rating count and not the rating count. But well, all that aside, it has all that data, right? It has the Goodreads book ID and all kinds of stuff. And it also came with a Jupyter Notebook file which had some exploratory data analysis already done for me, so that helped definitely. I read this article by I don't remember his name. I think, yeah, it was this article. So Adam Fontenot. So here he basically replied to another article which was using the Dirichlet distribution to model our data, and it also was modeling it for the average rating. And he criticized that. He said that the average rating can be modeled better using a beta distribution. And so he explained what he is doing, and then he showed his estimation for the distribution. And he didn't actually give any kind of simple explanation as to why this would be naturally occurring. He did give some motivation for why it would be happening in nature, but he didn't use equations and numbers and quantifiable things to make it more solid. And so when I was trying out how to fit a curve to this distribution, so this is just the histogram for average rating that normalized, right? Yeah. So when I was trying this out, I first thought about, is there a natural reason for why this histogram looks the way it does? And so I came up with my theory where we view books as a collection of traits. So now we can proceed to the thing that I actually did. So first, some interesting observations. The distribution of books according to average rating moves slowly towards higher average rating with increasing book count or rating count. And this is pretty obvious, like books with higher average rating are read more, right? When you want to read a book, you would certainly go for a book with a higher average rating. And so books that originally had higher average ratings, those will continue to have those average ratings, which is another point that I did. And they will grow in popularity much faster than the books with a lower average rating. So far I've been talking about average rating as a function of time, something that's dependent on time. But with my first point in my hypothesis, you will see that we can also think of it as an inherent property of the book. So for a certain book, the probability that a new reader gives it a certain rating is independent of the book's current average rating and number of rating. So say you have this book, and at some stage, at some point in time, you have so like this thing, this bar represents all of its viewers. So think of it as, you know, all these cells being individual viewers, and this bar uh, representing all of them at once. So some part of it, so maybe like this part, some part of it will be giving rating 1, some part of it will be giving rating 2, some part of it will be giving rating 3, and some part of it will be giving rating 4 and 5, right? So now as the book grows, all that happens is that these bars, they increase in length, but the ratio still remains constant. So this would be basically scaled up, and now these are the number of 1 ratings, and then these are the number of 2 ratings, and these are the number of 3 ratings, 4 ratings, and so on. So, you know, this is 3 rating, right? And so this continues like that. So you would get something like this, and if you let this continue to the origin of the book, so this is when the book was published, this is the flow of time, this is when the book was published, right? This is the flow of time, and these are, so there were y coordinates, or you could say range in our y-axis, because this is basically kind of like a range. So this is basically a range plot. So those things, our length of bars, those are the number of 1 rating, 2 rating, so on. So the edges of 2 sections, so like the point where they intersect, these points would follow a linear curve, I guess. And this is all just hypothesis. I have not yet proved that this actually happens, because I didn't have data that was you know, basically like how a book changes over time. I didn't have that kind of data. I only had the data of how the whole system changes as a function of time. Yeah, and this would also be linear, and so on. So you would get something like this. So at any given instant, this is your full profile for the book. You have these many 5-star ratings. Okay, this was actually 1-star ratings, I think. Yeah, these many 1-star ratings. Then you have these many 2-star ratings, these many 3-star ratings, 4-star, and this is probably the 5-star. Doesn't matter what order they are in. The thing is that these fractions stay constant. That's what I'm thinking. So how does this happen? When a person rates a book, I'm assuming that the person does it completely based on their opinion. So our masses and basically the audience of the book, that is kind of the same, right? Because they will basically read the book's description online, and then they will decide whether or not they are interested in the subject, and then they are going to go and read it, right? And they are also going to see the average rating and how many viewers, how popular is the book. But the average rating might influence whether or not they read it. It won't influence whether or not they rate it. If somebody truly believes that a book is bad, he will rate it bad. Doesn't matter what its current average rating is. And so what I'm saying is that these fractions stay constant, basically, because every time that you want to take another frame, so as time increases you take another frame, then think of all of these people over here as not having any idea how the book actually is. Some of them, some fraction of them, some fixed fraction of them will think that it deserves 5 stars, and then they will give it those 5 stars. Some of them will think it deserves 4 stars, so they will give it 4 stars, and 3 stars, and 2 stars, and 1 star, right? And yeah, this is a very important point in this whole article kind of thing I've written, because this is the basis of my assumption that we don't need to look at the popularity of the book. Sure, more time passes, this gets bigger, and then the more ratings you have, with more confidence you can say that the average rating is this, right? So what do I mean the average rating in this case? I mean the true average rating. So like we assume that time goes to infinity, then whatever fraction you will have, we are assuming it converges, right? So that fraction will be the true average rating, or I should say that fraction will give the true average rating, because here we're talking about the fraction of 1 star and 2 star and so on. So for every book you have an inherent property called the true average rating, right? And the more ratings it receives, with more confidence you can say that the average rating on the site is the same as its true average rating. And now I'll basically stop talking about it as true average rating and just talk about it as average rating, because most of the books had quite a high amount of ratings, so we can say with a lot of confidence that yeah, this will be the case, that its average rating is just that. Okay, so that's awesome. That was my first point, and you can also read all of that, but I won't be doing that. So how does this fit in with these observations? I mean, I just said that it doesn't matter what the popularity of the book is, right? But here you see that the more popular a book is, its rating actually increases. So that would lead to the conclusion that popularity does matter. But what I'm saying is that popularity as it increases, so you look at a certain level of books count, the distribution surely goes up. But for a certain book, if you did it for that book only, if you just did it for, like, if you actually had data for the book, how its average rating changes with respect to time or the rating count, then that stays constant. That's what I'm saying. Okay. And so yeah, this is not a contradiction to my theory at all, in fact. And this is pretty obvious. People won't read books which are poorly written, right? You would always go for a book with like 4.5 star rating. You won't go for a book with 2.5 star rating, right? Okay. So this is the first section. Popularity is a consequence, not a factor. That's done. Yeah, there's nothing more worth explaining over here, I guess. Okay, and now we enter into the second section, which is the distribution of books according to average rating. So here, this curve, this red curve, is just the histogram for average rating that you see over here, normalized. And we are fitting these two analytical functions, these two curves, to this red graph. So the green one is a binomial distribution, or I should say a binomial probability density function. And of course, since you have 50 times x minus 1 and stuff over here, it's a factor of 50. You have to add that at the top, at the front as well, because it's a probability distribution function. It should have area 1. Okay, and this purple or whatever color this thing is, that's the beta distribution. So for people who don't know about the beta distribution, it's completely fine. I won't be talking about this at all for most of the case. I will be talking about it at the very end when I have to use an approximation. But yeah, the beta distribution is fairly easy to understand, and I've also linked some online resources in the acknowledgement section. You can go there and you can understand what this thing is from those resources very well. Okay, so I won't be talking about this basically. Okay, so this is what we get. We can fit these two curves to our data. Question is why can we fit this binomial distribution to this? Is there a natural reason for why you would have a binomial distribution? So I developed a theory which says that the binomial distribution is in fact a good estimate all the time, not just for this particular case. So let's start. Books as a collection of traits. So a good book has certain traits like good cover, good content, correct tone, suitable graphics, etc., etc. So for a certain book, we have, let's say, 8 traits. So you are thinking of that as a list, right? For example, right now let's just take 6 traits. So A equal to 6. Okay, so let's just say that the first trait is like good cover. um, and maybe the second one is something like good graphics, so graphs and whatever. Let's not name all of these, let's just let that be whatever. So I just call them as trait 1, trait 2, trait 3, so on. um, so every trait is basically kind of a characteristic of a good book, and it may or may not be in a certain book, right? So the probability that it is in a certain book, that probability is independent of whether or not some other good trait is in that book, right? Because it could be possible that the writer had like good resources, he made graphical representations and all that, but his content was bad, right? Or the vice versa, or any case in fact, right? Or of all the 4 cases. So the probability that his graphs were bad, or his content was bad, doesn't depend on whether or not he actually made graphs, right? If his content was bad, it wasn't. So for every trait, you have a probability of it either happening or not happening in a certain book. For our case, we'll just assume that that these probabilities are all equal and equal to Q. So there's Q probability that you will have good cover, and there's 1 minus Q probability that you will not have a good cover, right? So you will have like a list of crosses and corrects over here, something like that. What's the probability that you're going to get, say, K crosses or K correct marks? So instead of K, let's just use A times X. So X would be the fraction of good traits that you have in your book out of all the good traits that you could have. So that probability is just given by the binomial distribution. It's just this thing, ACAX Q power AX and 1 minus Q power A times 1 minus X, and written using K, this would be ACK. So you are choosing K ways, so like there are ACK ways to get K correct marks, right? And for each of those cases, the probability is this thing, Q power K times 1 minus Q power A minus K. Now just substitute K equal to AX in this, you will get this distribution. Awesome. This is not a probability density function, this is just a distribution. Okay, so this is like the real probability that that you're actually going to get K good book traits, something like that. Okay, so whether a book has a certain trait is decided by its audience and not an unbiased professional. This is an important point, because this tells us that since the people are biased, like most of them will think that that a certain trait is there even though it's not. Does that make sense? So like, for example, if I was going to read some book on maths, then I would like search what is the best book, then I would select one best book, and at the moment I select that book, I basically create this judgmental thing, like thinking, where I'm thinking that yeah, this must be a good book, right? And so I won't judge it critically. I won't actually think about what's happening in the book. Once I'm done reading it, I'll say yeah, it was a good read, and I won't think about whether or not it actually was a good read, because it was my choice that I read it. And so people are biased when rating the book, because they have read through the book, and probably that's why they're rating it. If they're not read through the book, then I don't know, maybe those are like small cases. I have no idea. I'm not a person who reads books a lot, but if you think logically, this actually makes sense, right? I guess. So if something like that happens, then you would expect that Q would be a big number, right? So instead of Q being something like 0.2, that yeah, there's 0.2 probability that you would get this correct, right, for a book, it would be like 0.75 or something like that. Why is that? Because whether or not to put this correct, it's not judged by some professional, instead it's judged by the masses, right? So this X thing is actually, how do we get this? We just let a lot of people decide whether or not it has a certain trait, and then whatever those like people come up with, that maybe you gave it to 100 people who wanted to read the book, right? That's an important thing, that who wanted to read the book, you gave the book to 100 of those people, then you record their opinions about a certain trait, in that book, then they are biased, of course, because they wanted to read the book. Then what that means is that it will most likely than not get a correct for any trait. So your Q is bigger than 0.5 at least, right? I guess that's convincing enough. Okay, so even if it's not, I mean, we don't really care about what the exact value of Q is. For now, we're just getting a feel of what's happening. So we don't want to be surprised when Q values actually turn out to be very high. And in this case, they do turn out to be 0.75. That's the exact, not very exact, but like a good estimate of that value. So that's good. We have this probability thing. What do we do with it? So whether a book has a certain trait, okay, this I did, fine. So we know that Q is high. Another reason for most books being good, okay, that's, I'm not going to go on that, that's just a thought in my head. I've not been able to prove this thing. So let's just move on. Okay, let's go to the thing. While rating a book, a person considers whether a trait he considered desirable is present or not. Let's say like every user looks for 4 desirable traits. Why 4? Because the minimum rating is 1. So 5 minus 1 is 4. That's why we are doing this. So let's say that every user looks for 4 desirable traits, according to him, of course. If he thinks good covers matter, then he will look for it. If he doesn't think that, why would he look at that? And this is completely random. People are of all sorts. So I would say like the probability that what he considers are good traits are actually in the book, that is in fact just given by, okay, let's not think about good traits, let's just think about one trait. So probably that a certain trait which he thinks is like it should be there in a good book is in that book, that probability is just X because it has X good book traits. So let's just like assume that these good book traits are parameters that are like rated by professionals or something. Okay, so it has X good book traits as perceived by the audience. If that's the case, then the probability that he will actually like get a true for the question whether or not his desirable trait is in the book, that probability is just X, right? So X is the probability that he will give it correct for that trait, and 1 minus X is the probability that he will give it incorrect or wrong or like this cross thing for that certain trait, right? So for 0 of these traits he gives, so like, okay, that would be for one trait, of course. Now we are taking the case where you have 4 traits. So you know, a user looks not only at 0 traits, sorry, at 1 trait, he actually looks at 4 traits. So if he finds that, okay, the first trait is not there, then he doesn't give it the star that it would deserve for the first trait, and then he looks at the second trait, maybe the second trait is there, and then maybe the third trait is also there, and the fourth trait is again not there. So all in all, he would give it 3 stars. So when you have 0 traits, he gives it 1 star. So for 2 he would give it 3 stars. But then that's not the only way to get 2 desirable traits for a certain user, right? There are 4C2 ways of getting that, and so that can be generalized, and for any smallest number of stars or something like that. Okay, I wouldn't say that. For now we are using the capital S thing, which I'll explain. Okay, so for 0 of these 4 traits he gives 1 star, the minimum rating. Probability that n users give the book a total of S, capital S stars is this thing. So now you're thinking of the n users as not just, you know, individual users. Every user is another Bernoulli trial. So these are basically like trials of the book, whether or not that trait is in there, and which trait to choose is chosen at random completely, right? So the probability that a randomly chosen trait is in the book, that's just X. So basically we go for like 4n Bernoulli trials, right, where there are n users. So like the first 4 trials will be for the first user, then second 4 will be for the second user, and so on, right? And it can certainly happen that one user like gave it 2 star and other user gave it 3 star, and so we are merging all of these together so that it doesn't matter what amount of stars he actually gave. You just look at these as individual Bernoulli trials. So you have 4n of these. Then the probability that you will get capital S stars, or basically capital S minus n of good traits, right? So like these are sorry, capital S minus n correct things, right? Oh, this is for a equal to 6, I guess. This is like, okay, this list will be for the traits, of course. Over here the trials are different. Here the trials were with respect to the actual good traits that a book should have. Over here the trials are having its desirable trait being chosen at random, so I shouldn't use that notation. Okay, so once again we'll use like, let's just say 1 and 0, I don't know, something like that. So yeah, 1 and 0, or maybe I'll say black and white. So if he finds the trait is there, he will make this black, something like that, right? So maybe like the first user thinks that, okay, 2 traits were there, and he makes 2 of these blacks, the corresponding traits, of course. And then the second user thinks, okay, these 2 traits were there, and so on. So you get this list of black and whites. So the probability that you will get capital S stars is the same thing as the probability that you will get capital S minus n black boxes, which is just 4nc S minus n, that's the number of ways of doing this, times the probability for every case, like every arrangement of these black boxes, which is just x power S minus n 1 minus x power the remaining stuff is like 4n minus S minus n, and just write as dot to dot, basically this expression, right? So that's the probability to get capital S stars. And of course capital S stars, what does that correspond to? That corresponds to capital S upon n rating, so we'll call that as capital R. So this is the probability for capital S given n and x. Okay, here I'm assuming okay, here I'm thinking of every, okay, I already did that for the Bernoulli trial thing, fine. Okay, now we're finally getting to probability distribution. So for okay, also there's another important point, I guess, over here. Yeah, as n gets big, this curve gets narrower with peak at S approximately n times of 1 plus 4x. So I did all of this with a variable capital N because I wanted to say that as n gets big, this function, basically this function, this distribution, it becomes narrower and narrower and narrower. So like for n equal to 1, maybe it was like this. For n equal to 2, it became like this, and for n equal to 3, it's, I don't know, something like that. And so it becomes very narrow. So that's almost the same as saying that, yeah, this x value, right? So this is with respect to x, of course, right? Yeah, or should it be with respect to s? Oh, it should be with respect to s, sorry. So yeah, it's a binomial distribution in capital S. Okay, so okay, this s value is in fact how, okay, like this s upon n is actually what we should be looking for. Why one stop at s upon n actually convert to rating itself. So let's think of it as capital R. So for different n values, you will get different curves. For very big n values, this curve will be very narrow. So you could just say that, yeah, this book actually has this true rating. Although for n equal to 1, this guy's rating, its true rating could lie anywhere. In this case, as it becomes very narrow, this will be what its true rating should be, or does that make sense? So almost certainly its R value will lie somewhere over there. And what is this place exactly? Well, this place is this thing when you have x over there, right? Yeah, so R equal to 1 plus 4x, so this is actually 1 plus 4x, fine, because 1 is minimum and then 4, so that's why this thing, yeah, 4 trials, 4n times, makes sense, right? Okay, so 1 plus 4x is in fact where you will get a peak, and so what we'll say is that, yeah, its true rating is in fact just 1 plus 4x. So now we can proceed. Yeah, that was the point, in fact, that the probability that a book has rating R, given you have n of 4n of these trials, um, yeah, that is the same as the probability that it has okay, that's of course the thing. So yeah, it has r minus 1 upon 4a good book traits. That makes sense, I guess. This is given x, right? Yes, this is like given x, so you would also have x being a variable, then this sentence makes sense, I guess. Right. So all in all, what I want to say is that the average rating that you see on the site is in fact its true average rating. Once again, all of this is just getting to that point. And so now we can go into generating the books rather than seeing how the users rate those books. We'll see how we can generate those books. So we can forget about this capital N thing completely. We won't worry about how the users are rating it. So we can forget about this as well. And just focus on how we get an X value. So we just said that the probability that a certain book randomly chosen has a certain trait is Q, right? And from that we got the probability that it has X fraction of good book traits. So, and we also know that X is in fact just the same thing as its average rating on the site. I know it's approximate, but yeah, I'm gonna say it's the same. Average rating on the site minus 1 because it's the minimum upon 4 because the range is now 0 to 4, right? R minus 1 belongs to 0 to 4. That's why upon 4. So its average rating minus 1 upon 4 is in fact what X is. It's the fraction of good book traits it has. So now instead of thinking of this probability as a function of X, you can also think of it as a function of R, and from that you can get a probability density function. So first of all, we'll just put, instead of X, we'll just put this thing in there. So what you will get is something like AC, A times of X is just this thing, so like A R minus 1 upon 4 Q power AX, same thing as this guy, so A R minus 1 upon 4 and then 1 minus Q, and you get the idea, right? Yeah, so this is a function of R now, right? Given a rating on the site, which is a real number by the way, you can figure out what yeah, so like what's the probability that a randomly chosen book will have that rating. And this has a bit of a problem because over here AX should be an integer and X and R are real numbers. So what we need to do is only choose those values of R which actually gives an integers. So the way I will be doing this is just say that getting a fractional amount of, so like okay, a fraction number of good book traits is impossible. So you can have k equal to 1 2 3 0, okay, 0 is also possible, 0 1 2 3 so on, choosing from this A thing, right, a list of A good book traits. But you cannot have something like 1 by 2 2 by 3, things like that. So for 0 and 1 you will basically like get a discrete distribution kind of thing, yeah, but that can be thought of as a continuous distribution as well using the direct delta function. But let's not get into that because I have a better way of getting into the probability density function using approximations rather than discretizing and making it continuous and stuff like that. Okay, so in a range of capital R to R plus delta R, how many okay, like how many numbers of R values, right, how many R values will you actually have that give integer AX values? So X is this thing, then A times of X is just this thing. So like you vary R, then these must be integer values. Let's say you have found a number where this is an integer value, the next R value, the immediately next R value where this is once again integer, would be at an interval of 1 upon A, right? Okay, not 1 upon A, 4 upon A, yeah, because you have this 4 over there, so that's why you have to do 4, so multiples of 4 stuff, makes sense, right? So like say A times of R naught minus 1 upon 4 is an integer or a natural, actually a whole number, because we know it's not going to be a negative number. So then you also have, instead of r naught, if you just put r naught plus 4 upon a, this will be the next integer, right? So putting r naught plus 4 upon a over here, what you get is this same thing, right, plus 1, yeah, which is the very next integer. So r naught plus 4 upon a is the very next value where this happens. So in this range you will have these many of numbers which we can put in our expression to get a probability out. And because non-integer number of good books are impossible, we will only use these numbers. All the other reals will throw them out. So all these numbers will give almost the same probability if your delta r is small, right? And considering that you have a factor of 4 upon a over there, even if your delta r is small, you will actually get like some numbers out. So it's a good thing to do. I mean, it's a good approximation, right? All these numbers will give almost the same output. And what is that output? It's around p sub x of r minus 1 upon 4, because that's like the output for r. So it's also the same output will be approximately the same output will be for r plus delta r, right, if delta is small. So then the probability that you get you get the average rating of a randomly chosen book in this interval, that is given by this thing. So it's a upon 4 p sub x of r minus 1 upon 4, right, that common thing that we just talked about, and expanding that you just get this thing. Awesome. And with some hit and trial, oh, and by the way, this is in fact the expression we are looking for. This is the probability that a randomly chosen book lies in a interval r comma r plus delta r, where r is the rating. This is exactly what we have been looking for, the probability distribution function, or probability density function in this case, for r, right? And so with some hit and trial, I found that q equal to 0.75 and a equal to 50 fit the data good enough. So this is what I basically did. Yeah, it's Desmos. Now good, the weird thing is, like, we were not allowed to use code from other people, and I basically just used another software, so I don't know whether or not this was something that you could do, but well, now it's done. So yeah, a equal to 50, q equal to 0.75. This is what the graph looks like. Now changing a, this graph's height changes. So for big a values this gets narrower, and for small a values this gets spread out. So a equal to 50 is where it meets the curve quite a bit, and q equal to 0.75, well, you could have chosen 0.74 or 0.76. I don't know the exact values, I just went with it. Okay, so what looked good, and then I rounded it up to 0.75. Okay, this image is of course the one that I generated from the histogram, right? It's the same image as the last time. Okay, this function, this is basically our probability density function in r. Instead of r, I'm using x over there. Do not get confused by that, please. This x is not the same x as you see in my derivation. This x is actually supposed to be replaced by capital R. So yeah, I guess I made it a little confusing, but it's just a function in the end, so it doesn't matter. And this is a beta distribution, which is also which we can also approximate. So you can which we can approximate this graph with, but let's not actually get it. Okay, I'm just gonna show you the thing for x equal to something. So yeah, this is a good approximation, I guess, something like that, right? So yeah, this beta distribution also, okay, this is perfect. This is the approximation we're looking for. So a beta distribution might also fit, in fact. Awesome. And this is of course linked in that Notion page, so you can always play with it however you want. Okay, now this is good and all, but how do we use this? Yeah, we proved that, I wouldn't say proved, but we basically motivated that it can be estimated using binomial distribution. Can we do more stuff with it? Well, we can predict more stuff. So I want to predict the distribution for fraction of 1-star ratings and 2-star ratings and so on, and I'll explain what that is later. But first, and another interesting thing I noticed is that, I mean, which you all have noticed, of course, is that the binomial and beta distribution fit quite well. They are very close to each other. In fact, I'm gonna show you a bit of demonstration, and then you will like understand what I went through when I discovered this. So these are our two distributions. One is the binomial distribution, this one, this purple one, and this red one is the beta distribution. We are looking at q equal to 0.5. This is when in fact they are the closest. So yeah, s is there just to make the graphs easy on eyes. So you have this s equal to 1 upon square root of a multiplied for both distributions. If we remove that, it would be like some very big function thing, so that will like go out of the page. Let's not use that. Instead we do this thing. So for a equal to 100, this is what like the graphs look like. So q equal to 0.5, and the graphs are almost the same. And no, it's not like I'm not showing one of the graphs. Both are there, it's just they are overlapping. They are in fact the same at this point. And so when we change the q values, yeah, one graph follows the other. And you might say, okay, are they in fact the same? No, they are not. When you change a, you see that there's a bit of a gap between them. It's only for big A values that these appear to be same. So it's not like they are the same, they are approximately the same. And we can use this approximation to our advantage. And although I wasn't able to like write a formal proof for this, there are proofs on how both functions can be approximated as normal distribution. So I guess it is reasonable to assume that these in fact are good approximations. And if someone actually finds like a good proof of why these two distributions are so similar, please give me that proof. I need that. Okay, because while trying to prove this, I accidentally just rediscovered the normal approximation to binomial distribution and stuff like that. So yeah, quite complicated to prove this. I was able to get partial success in proving this, but that's about it. Partial. I wasn't able to do this for any general q value, only when x is approximately q. But this is what I came up with so far. So we know that the binomial distribution can be approximated as a normal distribution, and if you don't know that, don't worry, it doesn't matter, because this is like just one section, so not a big deal. So yeah, it can be approximated like that. Replacing x by q and vice versa, and replacing a by a plus 1, you can do that. It's approximately the same. So you do that, you basically arrive at the beta distribution on the left hand side. So this is like binomial of, instead of x you have q, binomial of q comma, okay, q given a plus 1 comma x, right, which is just this expression, right? So you replace q by x everywhere, you get this thing, and replace a by a plus 1, so you get this expression. And this can be approximated similarly as we approximated this expression. In the end, these are just numbers, right? So you can do this, you can approximate this by that, because we are assuming that x and q are not very close to the edges, because very close to the edges things go to 0 anyway. So they are not very close to the edges. If you assume that, then sure, you can do this. But even this approximation is not actually what this is. So we need to do another thing. We need to assume that x is either approximately equal to q, or it's approximately equal to 1 minus q. This is important, because with just q, you would like, so if say your q was like 0.75, somewhere over here, this is 0, 1, then the values of x for which this approximation would work would lie in this range. I don't know how big this range should be, but it would lie somewhere over there. But if this also works for 1 minus q, then you have this range and this range, which is basically this complete range. And so this works really good. And the more points where these are the same, because these are continuous functions, what would happen, a continuous function with good derivatives, what would happen is that, these would also be the same in any interval like this. So yeah, that is amazing. And so if we can just assume x is approximately equal to q and approximately equal to 1 minus q, then these two are similar. So what we just did is like kind of get a motivation for why you should or you could use this approximation binomial to beta. Also, when q is approximately 1 by 2, the beta PDF can actually be approximated as a normal distribution like this, which is exactly the same thing as this thing. And I've not looked into the proof completely, but there is a proof, and I was short on time really. So you can check that proof out. It's a stack exchange proof, I think. No, okay, it's on Wikipedia, fine, whatever. So yeah, thus in the case that A is big, our two curves are very close. So what we can do is, substitute the beta distribution for the binomial distribution at every, like place we can, so that things become simpler. And I'll show you why I want to do that. So fraction of S star ratings. First of all, given a book has XA goodreads, the probability that a user would rate it S stars is just this thing. Makes sense, right? You have 4 vulnerability trials, and small s is actually like, this is not a real, so small s is not in reals, it's in integers, of course. It's just 1 2 3 4 5, right? This is the fraction of capital N ratings that are S star ratings when n gets very big. So like, this is for one user. So if one user rates it, what's the probability that you would get small s stars? You just get this thing. And what does probability really mean? It basically means that when you let the sample size go to infinity, the fraction that you observe is in fact just this thing. So as n increases, which is the number of ratings, this is in fact the fraction of 1 stars. Awesome. So now this is a function of x, of course, that if the book has x fraction of good traits, then you will get this fraction. What we want is the expected value of our fraction. So what's the fraction of, like, okay, what's the how would I even say this, what's the expected value for the fraction of 1 star ratings, right? What do you expect? Where would like, how many, this is hard to explain without the distribution. So this is actually the distribution that I'm talking about. So yeah, just look at this and then you'll get a good feel of what I'm talking about. You have this data, this is the fraction of 1 star, and what I've basically drawn is or plotted is the probability distribution, and what I want is the expected value. So yeah, it's like the mean, you could say, in a way. I'm not gonna explain this, come on, that's something you can go for in like Wikipedia or something. Okay, so that gives us the expected value, this summation. But just look at this summation, it goes from 0 to A. In our case, A is 50, so that's a small quantity, but for ideal cases, A would have to be infinity, right? And so this would actually just become something like an integral. But let's not talk about that first. Let's talk about evaluating this summation itself. If you actually substitute f of x and p sub x of x, you'll get this thing, right? Okay, so this is the f is a function of x, right? The fraction of 1 star ratings for a book. Well, that times the probability that you actually get x good traits in a book, right? You have to sum up all of these kind of things, and that's gonna give you the expected value. That's just the way it is. So then expanding this, you will get this, right? Just substitute f of x and p sub x of x for their actual expressions. You'll get this summation, which is, I mean, it just looks scary. But then if you like use our approximation, what we can do is, first of all, we can approximate this as an integral, and then we can use our approximation to further simplify this. Even when you actually turn this into an integral directly, this is hard. This is an hard integral. You have only went from a hard sum to a hard integral. Nothing has changed. But when you try to, I mean, you already made an approximation. So when you approximate it further by replacing the binomial distribution with the beta distribution, this becomes this thing. This integral is very doable. It's very well known as well. It's just a beta function, isn't it? So this integral evaluates to this thing, right? And now we can approximate further. So what is this? Yeah, it's just this thing. So it's a plus 5 and all of that to the power of -1, fine. So just a plus 5 in the denominator. You got a plus 4 c qa plus s minus 1, which is a plus 4 factorial. upon qa plus s minus 1 factorial, and the difference, so that will just be a times of 1 minus q and plus 5 minus s factorial. That's what you get on the denominator. And what about this expression that you pulled out? It's this thing a, well, ac aq is basically a factorial upon aq factorial, and then a times of 1 minus q factorial, and you got this extra factor of 4cs minus 1, right? This is the expected value. Now this is approximatable even further, because aq factorial and you got this stuff over here. So like this factorial upon that factorial is approximately basically aq to the power of s minus 1, because when you write it out like explicitly, this would just be qa plus s minus 1 times qa plus s minus 2 and so on, right? And that would just be starting from aq. So when you divide these, like aq factorial just gets cancelled, and you just get the first s minus 1, okay, the first s terms, I guess. No, the first s minus 1 terms, yeah, terms, products, whatever, terms, yeah, that's what it is. So all of those terms are approximately aq, because s minus 1 is just a normal number, like 1 2 3 4 0 1 2 3 4, and this thing is huge because q, it's just a normal fraction, a is a big number, so this thing is huge. So like all of those numbers would also be the same. So what you would end up getting is something like, okay, that actually goes on the top so that you can write it nicely. What you will end up getting is just aq to the power of s minus 1, and this also goes on the top, and what you will get is just a times of 1 minus q, this to the power of 5 minus s. You still have that factor 4c s minus 1. Okay, what about this thing, a factorial, and this basically combines just a plus 5 factorial. We divide, oh actually, you know what, let's not even think about a plus 5, because these numbers are approximately the same, so you can just cancel them without hesitation. So just a plus 4 factorial upon a factorial, that's a power 4 approximately. So you just do that over there. Awesome. Now you can pull out these a, and you'll get like a power s minus 1, a power 5 minus s. Add these, you just get a power s minus 1 plus 5 minus s, which is a power 4. So you can cancel all of these a's out. So what you get is this thing, 4c s minus 1 q power s minus 1 1 minus q power 5 minus s. Things to notice, first of all, this is extremely easy to calculate. Q is just 0.75, a is not there, s is a normal number, integer in fact. So you just like 4c some integer and some whole number basically. Q power some whole number, q is just 0.75, 3 by 4 basically, just a nice fraction. 1 minus q is 1.4, the power of 5 minus s is something. So this is like extremely easy to calculate. You could even do it by hand or something, right? So yeah, so this could have like good applications. I don't know what applications it could have, but yeah, this is a good approximation as well, because you can see that from this graph. Expected values, so without approximation you get these values, which are, I mean, yeah, these are actually closer to the data, but not that much, in fact, not how we would like. And with approximation you get almost the same thing, yeah. Okay, so instead of this expression which you would need a computer to solve, now you get this expression which is doable by hand. And okay, in the end what you want is values. So for s equal to 1, what value you will get? You just get like 0.005392 from the original expression. You get 0.00390625. You might say, well, that's a factor of 3 by 5, it's not very good. But notice what happens as s increases. So for 2 you get 0.05 something, this is 0.04, this, and it's close to 5. It's just like, it's just 3 to something less, right? 0.0032 something less. Yeah, then you get 0.208152. Over here you get like 0.210935, which is close. Wouldn't you agree? It's close. You get 0.4 something, you get 0.4 something, you get 0.3 something, 0.3 something. So it's a good approximation, and you can see this visually. Okay, now that's good and all, how do these compare with the actual data? So this is the histogram for fraction of 1-star ratings, right? And these vertical lines are at x equal to our values that we calculated. So red line is for prediction, the actual without approximation thing that we should be doing, and this blue line is for the approximation that we did. So these two lines themselves are very close, but these are not close to the mean. So for case s equal to 1, this doesn't look very nice. S equal to 2, it does look very nice. It actually, yeah, works. S equal to 3 looks good, although it should be slightly over here, but this does look good. S equal to 4 still looks good, although it should be over here, so it's overestimating it, but fine. S equal to 5 is where it goes a bit bad. I don't understand what happened. Maybe it's like people just rate things 5-star more or something like that, or maybe there are more parameters I didn't take into consideration. But all in all, I would say that considering this explains quite a lot. Like, this is a good theory. In fact, first of all, it explains our main concern, which is our distribution for average rating, very well, and it also explains these things decently well, right? So I guess it's an acceptable theory. Okay, some unanswerable questions from my analysis. I couldn't prove my hypothesis about average rating approaching the true rating as a rating count increases, because we do not have time related data. I already said that before. Or maybe we do have it, I just didn't see it. I don't know. I actually like did it in a week completely. So yeah, I was short on time. Okay, libraries and the functions that I used: NumPy, Matplotlib, Pandas, COMB functions with a combination function from math, and beta.pdf. So weird thing, this doesn't actually take like any real number, it only takes integers. So like when I wanted to use something like gamma function and stuff, this wasn't working. I thought Python libraries were using like things for all real numbers, or I don't know. I get why it uses integers, because it's just easier to calculate. You don't have to do a whole integral to do that. But still, anyway, I'll use the beta.pdf directly from scipy.stats when I actually wanted to use like the combinatoric function for all real numbers. So that was libraries and functions. Finally, we have these two sections: references. So looking at the distribution of ratings on Goodreads, of course the URL that I post that I have before. I showed you this, right? Okay, binomial distribution, Wikipedia. So just the normal approximation. I actually didn't know of it before, and I had to learn about all of that. Beta distribution, Wikipedia. So once again, normal approximation. Okay, acknowledgements. So first of all, I want to thank Professor Shanmugar for providing necessary practice and exposing me and my batchmates to this topic and helping me improving the approximate. So like, okay, this is not like, okay, this practice is not related to helping me in approximate equality between binomial beta distribution. This is a completely different thing to that. So he provided necessary practice for using first of all, he set up labs so we could like get practice for using these libraries, and he was the one who actually gave us this assignment, and that's what exposed all of us to this data set. So without that happening, I would have never done this. So yeah, I thank him. Fine. And yeah, I actually met with him and we tried to prove that this approximation thing works. It was hard. Yeah, like we thought we had a solution, but we didn't actually get a solution, and in the end I just had to like make up 3 cases: q equal to 1 by 2, x approximately q, x approximately 1 minus q. It's not satisfactory enough. I want quantifiable, like I want like an I want to see how much is the error and how does the error behave, but for now I'm satisfied with it. Okay. I also want to acknowledge these online resources that help me teach myself Bayesian statistics and thus understand the article that I linked to. So yeah, I don't actually know Bayesian statistics that well. In fact, I'm just a first year BTech guy at IIT Gandhinagar, so I wouldn't know that, of course. But I was able to teach myself because of these nice resources online. and then I could understand Adam's article a bit, and that's why you have this thing in front of you. Okay, so that's it. I'll see you guys next video.